Welcome back. After looking at the economics of the PV systems, we will now look at the environmental considerations surrounding the PV systems. Why look at the environmental considerations at all? Well, one of the most important reasons for looking at solar as an alternative source of energy was to harness the clean energy from the sun. That is, we wanted to mitigate the energy shortage in the world in a cleaner way. So we should also ensure that the process of building these PV generators and system doesn't undo the good that they do in their usable lifetimes. But how exactly do we quantify the environmental impact of the PV systems? How do we measure if they are having a positive impact in their lifetimes? There are multiple ways of doing this. A lot of people try to measure the carbon footprint or the carbon emissions caused due to the manufacturing of the PV panels and then compare with the carbon emissions offset by the panels during their lifetimes. Another, more analytical approach is to look at the total energy spent in the manufacturing of the various PV panels or systems. Different manufacturing processes have different energy needs, and these are then compared with the clean energy produced by the PV systems over their lifetimes. Some experts also try to do a complete life cycle analysis, trying to trace the energy and carbon footprint of the PV panels throughout their lives, or as in more commonly known, from their cradle to grave. For the sake of this video, I shall cover the energy-based approach. I will first introduce some basic terms that are related to this approach. Let's start with the energy yield ratio. The energy yield ratio is nothing but the ratio of the total amount of energy yield of the PV system to the total amount of energy invested in its lifetime. As the PV yield depends on several factors like the size of the PV system, quality of the panels, the technology choice, etc., etc., it is possible to see a wide range of energy yield ratios when observed in practice. PV modules can have this ratio as large as 10 to 15, while PV systems will usually have smaller energy yield ratios. Now let's go to the energy payback time. It is defined as the total energy input over the lifetime to the annual energy yield of the system. Note that this shouldn't be confused with the system's economic payback period. Usually, the energy payback period of most systems is anywhere between 1 to 7 years, depending on the equivalent sun hours available in the place of implementation. Let's take a look at some of the PV technologies and how they fare in terms of the amount of energy required in their manufacturing. As there can be a considerable variance in the manufacturing processes, the graph shows the range of primary energy use for PV module manufacturing. As can be seen, the thin film technologies like amorphous silicon cost much less energy to be produced compared to the monocrystalline silicon, which can easily consume around 12,000 up to 18,000 kilowatt hours per kilowatt peak. Note that these numbers are often changing and would only read better as the manufacturing technology improves and the processes become more energy efficient. You must remember that the energy spent in the manufacture of the entire PV system would be more than required for the PV modules. However, it is difficult to allocate the exact energy cost to balance of system components like batteries and inverters, mainly because the technologies and manufacturing processes for balance of system might vary a lot across the variety of products available. Even so, there have been studies carried out to estimate the energy requirements of the whole PV system. In general, it is found that the energy need for the balance of system is significantly lesser compared to the PV module manufacturing depending on the PV technology and the balance of systems. The graph here shows the energy payback time for PV systems based on two different PV technologies, polycrystalline and thin film amorphous silicon. Also, the time taken to pay back the energy invested in manufacturing the PV module, the module frame and the balance of system is shown. It can be seen how regions of higher irradiance show a lesser energy payback time than the PV systems in the low irradiance areas. It can be seen that the module's energy payback time is smaller than that of the entire system. Thin film amorphous technology based PV panels pay themselves back faster in terms of energy due to their low energy manufacturing process. However, the balance of system for the PV system based on the same technology have a larger payback time, owing to lower yield of the amorphous silicon panels. In general, the energy payback time across technology and irradiance levels is seen to be between 2 to 6 years. I would like to remind you again that these fascinating differences in PV technologies can also affect the design choices at the system level, just like we had seen in week 7 in the modules block. The thin film amorphous silicon panels can work better under diffuse light. The crystalline silicon panels are more efficient, but amorphous silicon panels are less power intensive while manufacturing. So we see again that a lot of optimization is required at the system level to choose the optimal module depending on several factors. In summary, it can be seen how the energy payback time is much lesser than the PV module's lifetimes, which can be as high as 25 to 30 years. For the system discussed in the previous graph, the energy yield ratio are also anywhere between 4 and 10. Thus it can be said that the energy invested in the PV system manufacturer is paid back several times over during its lifetime. So we can conclusively debunk the myth that solar panels consume more energy to be produced than they generate throughout their lifetimes. Also, the European Union already has in place several recycling directives that have led to recycle practices in place for the large amount of crystalline silicon panels being used. There are studies that even indicate that up to 80% reduction in the production energy of the panel. This would further reduce the energy payback times of the crystalline silicon panels. Thus it can be said that the PV systems are beyond doubt net energy positive in their lifetime. So you have now seen the economic aspects and the environmental considerations of the PV systems. I hope you are now as convinced as I am that solar is the energy source of the future. Now, we only have one video left. In the final video, I will summarize the lessons we have learned in the last 8 weeks. I will share with you my final thoughts on solar energy. See you back in the last block.